going back in time, thinking about 19A, or even pre-calc, thinking about domain, if I had a function that looked like the square root of 9 minus x squared, do you know how to figure out the domain on that? And it's okay to say no.
3.
So 3 is involved in the domain.
Oh.
That is true. 3 is one of our extremes
And
of the
negative
domain.
3.
Yeah. And to get that 3 and -3, you probably did that in your head. But if I wanted to do that kind of algebraically, when I have a square root, I know that what's underneath the square root has to be greater than or equal to 0. And then that's where we would get the -3 to 3 from that. I usually do that by factoring. Some people can just do it in their heads. But this is the region where we get non-negative answers under the radical. And then just other things that can go wrong with domain. 19A style, there were really only 3 things that could go wrong. And the same 3 things are all that can go wrong in 19C. So I can't have a negative under the square root. I can't divide by 0. So if I had something like x over x minus 3, it's okay to have a 0 on the top, but I can't have a 0 on the bottom. So here in terms of my domain, it would be everything except 3. I could write that as -infinity to 3, punch a little hole, 3 to positive infinity. And then the other one that shows up for us is logs. So if I had a function that looked like the natural log of, I don't know, x squared minus 1, then in terms of a domain piece, that's telling me that x squared minus 1 has to be strictly greater than 0. So I can't take a log or natural log of 0. It's got to be positive. So in this case, if I were to factor that, that kind of looked like an or equal to, and I got to get rid of the or equal to part. It's strictly greater than 0. And if I do a quick number line on that, just a little bit. If I do a quick number line on that and I think about test numbers, if I plug in 0 for x, I get a negative number overall. So it's actually these outside regions that I would want here. So I'd have -infinity to -1 and 1 to positive infinity.
How do you make the test again?
So I put all of the values on the number line that actually make it equal to 0. And then test numbers in between. So in this case, I could test x equals 1, x equals 2, and x equals -2. And think about plugging those into the original constraint on the domain. So if I plug in 0, 0 squared minus 1 is negative. So I would not include that middle region. But if I plug in 2, 2 squared minus 1 is positive. If I plug in -2, -2 squared minus 1 is also positive. So these guys work, but the one in the middle does not. In terms of what's happening with the domain, I'm still thinking about the same things for our constraints on the domain. So in this case, it doesn't matter what I put into the numerator. I can put 0, positive numbers, negative numbers, but into my denominator, I know that x squared minus y cannot be equal to 0. It could be negative, it could be positive, it just can't be 0. I can't divide by 0. Well, this doesn't lend itself to putting something on a number line because this is talking about both x and y values. So one way that we sometimes show the domain is actually sketching a graph. So if I think about this, that's the same as saying x squared cannot be equal to y. So a sketch of that domain would end up looking like drawing y equals x squared. And then to show that it cannot be equal to, We make that a dashed line. So I'll just redraw that in with a dashed line. And then we shade in the rest of the plane to say that all other points in the plane give valid values of the function. In terms of stating the domain, we haven't really gotten to my worksheet yet. We'll get to my worksheet. But in terms of stating the domain, it's really just talking about all of our points X and Y such that whatever constraint we have to put on it is true. So in this case, for a natural log, I know that 2 minus X minus Y has to be greater than 0. And I could rearrange that to look like 2 minus X is greater than Y. And then think about what would that graph look like on an XY plane. So on the XY plane, the graph of Y equals 2 minus X would be a line that kind of looks like that. But because it has to be greater than, I'm going to put in a dashed line. So there's 2, there's 2. And then I need to shade the side of it that matches our constraint. So if 2 minus X needs to be greater than Y, I can choose a test point. So if I were to choose 0, 0, if I plug that in, the question is, does it make it true? So is 2 minus 0 greater than 0?
Yes.
I think it is. Which means that's the side that I'm going to shade because that makes the constraint true. Now I will point out this is backwards from when we were shading in the linear, in our linear programming problems, because there we were excluding the region that we couldn't include. And typically here, we show the valid region by shading it in. So it's kind of backwards from how we were doing the shading before.
How can we determine the bigger or smaller than, or it's always bigger than 0?
So for natural log, it's always that what's inside is greater than 0. If it were a square root, then it's everything is greater than or equal to 0. Yeah, so the same 3 rules for domain from 19A or pre-calc still apply for 19C stuff.